All right, folks. Hi, folks. How you doing? This is Trig Word Problems Part 2. This is a continuation. We did trig problems at the end of Unit 6, but all those trig problems created a right triangle. So we could do SOHCAHTOA. Now we're adding into the mix. How can we do trig word problems where we would do the law of sines or the law of cosines? So not necessarily not necessarily SOHCAHTOA. Couple of hints. Decide if you're going to look at this story from the top view or from the side view. This probably is the part that kids get mixed up the most. Think about in this story, are you measuring how high things are or how far apart things are? So that's usually kind of maybe a good guide there. I don't have a great way to say it, but you want to try to decide, am I looking at this story from the side or am I looking at this story from the top down like a map? Then you always start with the most permanent objects and go to the least permanent objects, and then don't put in any numbers until after you've drawn everything. So just a quick reminder, how do you know? Well, let's do the first example, and then we'll go back and talk about how to know the difference between a law of sine situation and a law of cosine situation. So Moana and Maui are 10 miles apart in guard towers on the edge of a seashore. Both can see Taka out in the water. The angle between the coastline and the line of sight between Taka and Moana is 35 degrees. The angle between the coastline and the line of sight between Taka and Maui is 45 degrees. How far is Taka from Maui? Okay, so don't worry about the numbers. Just think, what are the things that are happening in this story? What are the permanent objects, or just the objects? So we've got Maui, and we've got Maui. Moana and Maui are in these guard towers. So we've got two guard towers. We've got the edge of the seashore. So don't ignore physical things because they seem like they're obvious parts of the story. We still have the seashore, which means we have land, and we also have what? Water. And then we have this Taka creature out in the water that's attacking the land where Moana and Maui are guarding. So what's the most permanent of those things? I would say the most permanent would be the shoreline and the water. So let's start off by drawing. This will be the shore. Now, the next thing we said was there was water. So this side will be the water. So I would say the next most permanent things after the water and the shore is the guard towers. Those are tougher to knock down. Taka could move away, but the guard towers are going to be pretty permanent. So we have two guard towers that are, I didn't talk about this first. Is this a top-down or a side view story? So we're trying to figure out how high things are. Does it ask us how tall is Taka or how high are the guard towers? No. This is asking us how far apart things are. So usually that's a top-down view. So I'm thinking about this as a map, like I'm looking at a map. Here's the shore, here's the water on my map, okay? Next, I want to figure out, so let's put the guard towers. The guard towers are on the edge of the water on the shoreline. So here's one guard tower. And let's put Moana in this one. So I'm going to write M and O in there. Then we also have a guard tower where Maui is. Maui is guarding this end of the beach. So I'm going to put an M and an A in there. Lastly, we have Taka. Taka is out somewhere in the water. So I'm just going to pick some point. Let's say right here. I'm going to use that as the letter T. There's Taka. He's somewhere out in the water. Now, maybe he's not in the middle of those two. I mean, he probably is, but we'll leave it at that for now. Okay, notice I drew everything first, and now I'm going to try to put in some numbers and try to make the story really come alive as a picture. So Moana and Maui are 10 miles apart in the guard tower. So that's something that I can add to my picture. So from here to here, This is a distance of 10 miles. What else do we know? Both can see Taka out in the water. So, yep, they can both see him. The angle between the coast and the line of sight between Taka and Moana is 35 degrees. So the line of sight, when we say that phrase, that means from where Moana is, looking directly out to Taka. That's called the line of sight. So the angle created between the shore and her line of sight is the 35 degrees. So there's my 35 degrees. The angle between the coastline and the line of sight with Taka and Maui, so Maui has his line of sight, goes from here. The angle between the coastline, so here's the coastline, and the line of sight, there's the line of sight, so that means this then, that angle created there is 35. No. Taka and Maui is 45 degrees. How far is Taka from Maui? So now I can finally put my variable in there. What's the thing that we don't know? We don't know how far apart Taka is from Maui. So I'm going to call that X. All right, so whenever you're trying to do, we're trying to decide, is this a law of sines or a law of cosines problem? Here's kind of the two hints. Law of sines, law of sines always involves two angles and two sides. Now, when I say involves, it doesn't mean you have to know two angles and two sides. The story just has to be talking about two angles and two sides. One of those is probably going to be one of them has to be an unknown. The law of cosines, you're going to do the law of cosines when there is one angle and three sides. So I usually look to see if I have three sides in my story, and if I do, I know it's going to be law of cosines. If I don't, then I know it's going to be the law of sines. Most story problems are law of sines or can be done with law of sines. So let's see, I have a side that I know, I have a side that I want, but I don't know anything about the other side. So this is going to be a law of sines scenario. So law of sines, you always have to take the angle. Let's start to set it up. So you take the angle and the side opposite. So the sine of 35 degrees over x is equal to, now because this is the one that has the variable, this side I have to know the angle and the opposite side length. Well, 45 is opposite a side length I don't know. The side length that I do know is opposite an angle that I don't know, but it's an angle that I can figure out. Because what do we know about all the angles in a triangle? They always add up to 180. So I could take 180. I can subtract off the 35. I can subtract off the 45. And that leaves that other angle as 100 degrees. So now, sine of 100 degrees over 10 miles. Now I have got to set up a law of sines that I can solve. So we would solve this using cross mult. And that would leave me with 10 sine of 35 degrees equals x times sine of 100 degrees. Who's keeping x from being by himself? Sine. How do we get rid? Division. So I would figure out from this that x is approximately, so I want to do 10. I'll do fancy calc. 10 sine of 35, close it, over sine of 100, close it. Now, what are those in? Degrees. Check your mode. Yep, I'm in degree mode, so I'm good to go. I got 5.82. Now let's take this and put it back into our story. Since this is a story problem, we should answer with a short sentence. I'm not looking for the moon here, but I do expect one thing: units. Make sure that you're including your units. So the question was, how far is Taka from Maui? I would say Maui is about 5.82, what are we measuring in? Miles from Taka. So I'd like you to read example 2 and decide, is this a side view or a top view story? All right, so pause it if you haven't and read it. All right, a plane leaves JFK, travels due west at 570 miles per hour. Another plane leaves at the same time, travels. I'll talk about what that means. That's read north 22 degrees west at a rate of 585 miles per hour. How far apart are they after 2 hours? So in this story, does it talk about how high anything is, how tall anything is? Does it talk about the angle of elevation? No, it doesn't talk about any of that stuff. It talks about going west and it talks about going north and west. So that's a measure, that's a story of a top down. So I'm looking top down at this story. Okay, so what are the physical objects? We've got the airport, we've got the plane, we got 2 planes. We got the airport and 2 planes. That's it. So let's start off with the airport. I'm going to choose to draw my airport over here. The first plane, pretty straightforward how that one drives. It flies directly due west. So from here, it goes directly west. I'm going to call that plane A. Plane B is a little sneakier. Plane B, this is read north 22 degrees towards the west. So it means if you were going directly north and you turn 22 degrees towards the west, that's the angle at which you're going. So we would start off by drawing perfectly north. And then I would curl 22 degrees towards the west. So it would look something like this, where this angle here is the 22 degrees. That's what that notation means. North, going from north towards 22 degrees towards the west. That's plane B. The question is, how far apart are they after 2 hours? So I want to figure out how far apart these guys are. That's my variable. That's the unknown. In the story. Notice I didn't put any numbers in except for that 22 degrees so I could explain to you how that worked. Now let's see. So, okay, 570 miles per hour, that's not a measure of distance. That's a measure of speed, of velocity. So how far apart are they? We're going to have to figure out how far apart they've moved in general. Well, the first plane, remember, it's going at 570 miles per hour for how long? For 2 hours. So if I'm going 570 for 2 hours, I would take 570 times by 2. That would tell me that this plane has gone 1,140 miles in those 2 hours. My other plane is going at 585 miles per hour for 2 hours. So that goes a distance of, I'm going to go, I wish I would use purple for both of these. So this plane has gone 1,170 miles for its 2 hours. So right now, I can tell this is going to be a law of cosines problem. Because how many sides do I know / want? 1, 2, 3. But I do have to find one angle. So somehow you're going to have to find one angle in this story. Do you see it? Can you see one angle that you could actually figure out the value of? I found it. Remember, one plane went due west, The other plane started due north and then went 22 degrees towards the west. That means that I can now figure out that angle because these two angles together are complementary. I don't know if I should say together. They're just complementary angles. So these two angles should add up to 90 degrees. So if I take 90 and I subtract off the 22, we get 68 degrees. So I got one angle in this story, and I've got three sides. That means I'm going to set up a law of cosines problem. So law of cosines, you start with the side length that's opposite the angle. So for us, that's x squared is equal to one of the legs plus the other one minus 2 times the first one times the second one times cosine of, our angle is 68 degrees. I can plug and chug at this point. 1140 squared plus 1170 squared. Subtract 2 times 1140 times 1170 times cosine of 68. We already checked our mode, right? So I know I'm in degrees. Whoa! Big number, huh? Why is that not my answer? I don't feel like writing them both down. Why do I know that's not my answer? That's still x squared. So now I need to take that answer and square root it. I don't want to type it in, so I'm going to go square root, and I'm going to use the answer button on my calc. So that number is a lot more manageable, 1,291.98. So x is approximately 1,291.98. And because this is a story problem, let's make a little, not a long story answer, but just maybe a one sentence, one statement. So the planes are about 1,291.98 miles apart. So it looks like I gave an example that I didn't keep track of. I gave a little example on the side here of how that degree thing works. So here's a little extra example. Make a sketch of west 32 degrees south. Here's your starting point. What would west 32 degrees south look like from there? All right, so I would go directly west with a dashed line. And then I would take that dashed line and I would curve 32 degrees towards the south. So there would be a 32 right there. Let's have you try to draw this, go through, and actually just see if this is a side view or a top view. All right, so hopefully you read it and thought it through. Jack measures the angle of elevation to his friend on top of a building as 22 degrees 45 minutes. Jill, who is 12 feet closer on a straight level path, measures the angle of elevation as 42 degrees 12 minutes. If Jack wanted to hit his friend with a snowball, how far would he have to throw it? So here I can tell right away this is a side view. I'm talking about angles of elevation. We've got people on top of buildings. I can't look at that from the top down. I've got to look at that from the side. All right, so what are the permanent objects in the story? We've got Jack and Jill. We've got the friend on top of the building. We've got the level path, and then we've got the building itself. So I've got 5 things that I would try to draw here. Let's start off with the most permanent. I would say the most permanent in this story would be the ground, the level path that Jack and Jill are standing on. So I'm going to draw that first. This is the ground. So we have 5 things to draw. We have 3 people and a building. What's the next most permanent? hopefully you noticed too that the building was the next most permanent thing. So over here, I'm going to draw a building. And then I would say all the people are a tie. So any one of those people you could consider as being the next most permanent. So I'm going to draw a friend on top of the building. I'm going to make it real easy. Friend's going to be a dot. And we have Jill. And then we have, oh, wait a minute. Who's closer, Jack or Jill? Jill is 12 feet closer. So when I draw Jack, he's going to be further down the line. That's going to be Jack. And then we have Jill, who's a little bit closer to the building. Notice I haven't put any numbers in yet. I haven't even tried to draw my triangles yet. I'm just drawing the physical objects. Jack measures the angle of elevation to his friend. So the angle of elevation to the top of the building, that's where Jack looks from where he is, and he looks up. That means then that this would become the angle of elevation. So that angle of elevation is given to us in that weird sort of format where they tell us the minutes. So let me just do a quick review of how to handle minutes. That would be the same as 22 plus 45 minutes is out of an hour, and there's 60 minutes in an hour. So 22 degrees plus 45 out of 60 minutes, we would get 22.75 degrees. So Jack is operating at an angle of 22.75 degrees. Then we have Jill, who's 12 feet closer. So let's draw that in there. So the distance between Jack and Jill ends up being 12 feet. And then Jill measures her angle of elevation to be 42 degrees 12 minutes. So let's figure out what that is first. That'd be 42 degrees plus 12 minutes out of 60 minutes, which ends up being 42.2 degrees. 12 divided by 60 is 0.2, or 1/5. Now here's the question. Where is Jill's angle of elevation? It's tempting to write it here because that's in the obvious triangle that we now have. That is incorrect. The angle of elevation is always based off the horizontal and then looking up. So this is her angle of elevation. That's 42.2 degrees. Do we know anything else? Oh, let's try to figure out what we want to know. How far would Jack have to throw the snowball to hit his buddy? So Jack would have to throw this distance right here. I'm going to call this then. We'll call this X. All right, so do we have, how many sides do we have? We have one side known and one side that we want. We definitely don't have the other side, so this is going to be a law of sines. That means I need to figure out angles in the triangle, at least two of them. I would argue I could find all three of them. So let's first start with which one, this one's the last one. How could I find this angle right here? Well, we know that angle is 42.2. These two together make a straight line, so they must be supplementary. A full angle adds up to 180. A straight line adds up to 180. So I'm going to take away the 42.2. That leaves 137.8 degrees. For that triangle, for that angle in our triangle. Now that I know those two, I can go figure out that last angle, that third angle, because the angles in the triangle add up to 180, so that would be 180 minus 137.8 minus 22.75. We get 19.45 degrees. 19.45 degrees. And that's enough info to set up a law of sines on this. So let's see here. Let's set it up based on the angle that we don't know. So, or sorry, that's the side that we don't know, which is x. Sine of 137.8 degrees over x is equal to, now I got to use an angle and a side that I know. I know this side length is 12 and its angle is 19.45, so I'm going to use that one. Sine of 19.45 degrees over 12. This is something I can solve on my calc. I don't need to show any work. I would cross multiply and then divide. So I would first multiply the x up there, and I'd multiply the 12 up there, and then I'd divide by the sine. So this would end up looking like 12 times sine of 137.8, and then I need to divide off the sine of the 19.45, and we get 24.2. And like I said on the other ones, let's turn this into a story. I'm going to go back. I think it's better to always add the units whenever we get to an answer that has units. All right, so a quick little sentence. Say something like, Jack must throw the snowball about 24.2 feet. There's a nice little quick, succinct write-up instead of just saying 24.2. All right, last example for this whole section, actually, isn't it? Yeah, this 7.8 is the last one. A tree leans towards the sun at 6 degrees from vertical. The tree casts a 20-foot shadow, create an angle of 35 degrees from the end of the shadow to the tip of the tree. How far is it from the base of the tree to the tip of the tree? All right, let's talk permanent objects. A tree leans towards the sun. That casts a shadow. Now, it doesn't say it, but if you cast a shadow, you must also have the ground. So those are the objects that we're going to draw. What's the most permanent of those? I would say definitely the sun is the most permanent of those objects. So I'm going to draw the sun over here. And that's what you get. That's about as good as artistic as the level of art that you'll get out of me. Then we've got the ground. Okay, the ground would be, I would say, the next most permanent object. And then we've got the tree. Now tell me about this tree. This is a tree that leans towards the sun. So I'm going to over-exaggerate. It's only 6 degrees from going straight up and down, but I'm going to over-exaggerate my tree. The tree is leaning towards the sun. Now, the sun hits the tip of the tree. That hits the tip of the tree, and then it carries down to this spot here, and it creates a shadow along the ground. Anything? Nope. That's all the physical stuff. So now we can start to add in some of the story. All right, so the tree leans 6 degrees from vertical. So that means if you went directly vertical from the base of the tree, our tree is off of that by 6 degrees. So this here is 6 degrees. The tree also casts a 20-foot shadow. So we know that this has to be 20 feet. Creates an angle of 35 degrees from the end of the shadow. So there's the end of the shadow to the tip of the tree. So the angle there is going to be 35 degrees. So here, this ends up being 35 degrees. And then don't forget, we've got to put an X somewhere, the thing that we're actually trying to solve for. The question is, how far is it from the base of the tree to the tip of the tree? So we can't say how tall the tree is because it's on an angle. That's a little bit confusing. So that's why they're using that phrasing from the base of the tree to the tip of the tree. But it is, if you chop down that tree, that's how long that tree would be. Okay, let's look. Law sines or law cosines? This is law sines because I don't have that third side, nor do I want it. So I don't care about this over here. I want this side. I know this side. That's two sides. That's going to be a law of sines. But that then means I need angles. So I have x, side x. I have the side length or the angle across from side length x. But I don't have either of the angles. So see if you can figure out one of those angles. One of those angles should be a dead giveaway. All right, the angle that should be a dead giveaway is this angle right here. This angle right here is a 90-degree angle, the vertical, and then the extra 6 degrees off of vertical. So this angle is 96 degrees. Now, let's say that our story, instead of our tree leaning towards the sun at 6 degrees from vertical, let's say it leaned away from the sun 6 degrees from vertical. So instead of adding 6 to 90, we would subtract 6 and have 84. Just so either way, that story could go either way. Be prepared for both directions. Now, if I know two of the angles, I can figure out that third angle. So that would be 180, subtract the 96, subtract the 35. So this angle up here, this is 49 degrees. All right, let's set up a law of cosines on this now. So that would look something like law of cosines. I meant law of sines. So I'm going to start with the side that I want. That means I need the angle, sine of 35 degrees, over the angle, which I don't know is x. Sine of 49 degrees, over the side that I know, which is 20. I've solved a lot of these, so I'm not going to show my steps. If you need to cross multiply and show your work so that you get the right answer, go for it. I'm going to use my fancy calc here. So the 20 is going to get multiplied to the top with the sine of 35, and then we're going to divide off the sine of the 49, get 15.2. So x is approximately 15.2. What do we use, feet? So let's do a little write-up. We would say something like the tree is about 15.2 feet long. I don't want to say tall because that implies that it's going straight up and down, but we could say long for sure. All right, folks, that's it for 7. Take your time when you draw the pictures. Start off with the most permanent to least permanent objects and don't put in the numbers until the very end. Good luck.